Did you know that there are significant similarities between the structure and strength of wooden and plastic 3D printed parts? Today, I'm going to demonstrate this with some destructive testing to help you optimize the strength of your 3D prints. Anyone who's completed a woodworking project knows just how important it is to correctly orient the direction of the grain. Well, 3D printing is much the same. So in this video, we're going to compare the two. This is an expansion of a snippet in a previous video I did a couple of years ago. But this time we're going to explore the idea in much more detail. And we're going to start outside with this. Anyone who's ever chopped wood with an axe will intuitively know this. And that's that there's a right way and a wrong way to efficiently break down a log. If we strike our log with an axe from the right angle, we'll see that it cleaves perfectly in half, which is immensely satisfying. If the timber is nice and dry, we don't even need a lot of force, it still splits nicely apart, although it is a lot more enjoyable to give it all you got. Turn that same piece sideways, however, and it becomes immensely difficult to cut through cleanly. This is really not fun. But if we turn that same stubborn piece up on its end, we can cleave it successfully in half, much to the detriment of the tripod. So why is this, and how exactly does it relate to 3D printing? To explain this, we need to look at how trees grow, and we're using this excellent time lapse of the early days of an avocado tree growing from a seed. I want you to pay close attention to the thickness of the stem that will later become the trunk of the tree. You'll notice that despite this plant growing vertically quite quickly, the stem of the plant more or less retains the same diameter. Yet we know that eventually, this avocado sapling will grow up into a much thicker trunked tree. So as well as our vertical growth, there has to be a means for the trunk to gain thickness, and it does this by growing additional layers over time. Here is a cross-section of a tree branch, and most people understand that the rings on this indicate a year of growth. But what most people might not understand is that the color variation that makes the rings comes from the different seasons and different temperatures at that time of the year. Underneath the protective layer of the bark exists the cambium layer, where the external layers of the tree are added to each year. If you're wondering about the color variation, the inner sections are called the heartwood, and they're not really doing anything for the tree's growth. The sapwood on the outside is the active layer carrying the moisture up and down the trunk. And interestingly enough, if we look at the cross-section of a tree under the microscope, we can see that it's primarily hollow, with many passageways for this moisture to go through. And if instead we look at a cross-section of timber from the side, the pattern left behind from these pores is called the grain. Now we'll examine our tree, breaking it into segments, and if we zoom in, we can see that we have continuous vertical growth that is stacked in layers radiating outwards. Would you be surprised if I told you that the structure of FDM 3D printing was much the same? Like the vertical growth of the tree, when printing, we have portions of plastic that are extruded in one continuous movement. And it's the stacking of these continuous extrusions that makes our machines capable of producing 3D parts, as opposed to their 2D brethren. Again, we can represent the process in a diagram, highlighting that some parts of the process are made from continuous extrusion, but then these are stacked in layers, this time building vertically. It's the same concept, just flipped 90 degrees, with trees stacking layers outwards in X and Y, whereas 3D prints stack their new layers vertically and have their continuous growth or extrusion in X and Y. To demonstrate why these similarities matter, let's conduct some destructive testing. To do this effectively, we need something a little more repeatable than using an axe. So here we have a piece of Australian hardwood called Jarrah, which is known not only for its looks, but also for being very dense and very tough, ideal for furniture making. And what I did was take a table saw and take a series of slices off this single piece, with half of them being cross-cut, that means cutting across the grain, and the other half being ripped, which means cutting in the same direction as the grain. That gives us some samples for destructive testing with a clear distinction. Our cross-cut pieces on the left have the grain going from side to side, which means what you're seeing on the large flat sides is end grain, and our pieces on the right that were ripped have the grain running vertically along the longest length of the timber. To match this with FDM 3D printing, I took this simple rectangular prism and printed a series of them, with half of them laying down flat and the other half standing on their smallest side, oriented vertically. Much like the timber, that gives us a sample set on the left, where the layer lines go horizontally, and a sample group on the right, where they're extending vertically. I clamped each sample on the corner of my workbench, measuring to make sure they had the same amount of overhang. The 3D printed parts were smaller, but again, the overhang was measured with the ruler to keep things consistent. My test involved dropping a series of weights, always aligned with the top of the clamps, and some foam packaging underneath to catch the weights as well as any bits of debris. Let's start by testing the timber where the grain is running along the piece, and as you can see, a 2.5 kilogram weight has pretty much no effect. We need to upgrade to a 5 kilogram plate before we get a result. So what about our cross-cut piece where instead we're attacking the end grain? Well, as you can see, the 2.5 kilogram weight destroys it. In fact, we don't even need any weight. Our finger is sufficient to easily break it in half. Back to trying to snap the grain, and our finger has no effect, either does punching. It's clear, as our chopping wood with an axe suggested, that our piece of timber is much stronger in one direction than the other, where it snaps quite easily. If we revert back to our earlier diagram, we can see that it's much harder to break the grain of the timber, but it's relatively easy to split it apart. So how will our 3D printed test pieces fare? The first thing to point out is that they're printed nearly hollow to remove the influence of infill strength. We start again with our continuous extrusion, going from left to right, and we keep increasing the weight until we have a crack or an abysmal failure. The strength of these parts varied, with the strongest being able to withstand 1 kilogram. Our low layer died with a 250 gram impact, 2 others broke with half a kilogram, the next 2 broke at 1 kilogram, and then we have our invincible test piece, which I couldn't seem to break. So how about our other samples where instead our extrusion is going across the part and we're effectively breaking apart the layer lines? I used the same testing procedure, starting out with 250 grams and then increasing that to 500 grams as necessary, stopping when a failure was reached. And as you can see from these results, the parts printed in this orientation are significantly weaker than those printed lying flat on the bed. Just like the timber, our portions that were created continuously are quite hard to break, but those that have been stacked later on are much easier to split apart. Before we move on, let's examine exactly why the strength between 3D printed layers is so much weaker. Our nozzle is hot, and therefore as it's extruding plastic, that plastic comes out at the same continuous temperature, meaning it's more or less one piece. If we use a thermal camera, we can verify this, and we can see that the top of the model where the extrusion is taking place is all the same color and therefore temperature as it's deposited. But watch closely what happens to the shape on the left as the printer moves over to the right hand shape to add the next layer. In a matter of seconds, it cools down dramatically, and it's not long until the infrared camera shows it in purple, which means it's even cooler than the bed, which at its hottest is 60 degrees Celsius. In the footage you just saw, the continuous extrusions were all done at 220 degrees Celsius, and as such, each segment of the line is well bonded and very strong. Conversely, when we come back to add a new layer, we're still printing at 220 degrees Celsius, but we're bonding that to the previous layer, which is now cooled to ambient temperature. So the bond and therefore the strength is inferior. So what can we do to ensure maximum part strength? First and foremost, the most important decision we make is when we're placing our object on the bed in the slicer. Anything we print will be significantly stronger in the XY direction rather than the Z direction as we add layer lines. So all else being equal, the best thing we can do for a print is to lay it down flat on the bed, which also has the bonus of being much faster to print. So what if you're designing your own parts and you've got a particularly tricky part? Let's say for this fan duct and mount, we place it so this surface sits flat on the bed, put some support material under the left hand side, but then we're stuck with the situation where the rest prints vertically and it's most likely going to be fragile. In this case, I would suggest the best solution is to split this part into two. This means both parts can be laid relatively flat, and we're not really compromising strength for either part. Let's say our hands are tied with part orientation, so what do we have left at our disposal to increase interlayer adhesion? Our first options are to increase the temperature at which the molten filament is laid on top of the previous layer. So that means increasing the nozzle temp, turning down the part cooling fan, or even printing inside an enclosure. Keep in mind that these solutions also have downsides, such as the excessive stringing seen on the hottest band of this temperature tower. This temperature tower was generated from my free calibration website, It is an excellent tool for working out the best compromise between strength and appearance when experimenting with nozzle temperatures. In addition to this, we have options such as increasing the width of each individual extrusion, which will increase the contact patch between each layer. We can also slow down the feed rate, which should increase the transfer of heat from the nozzle down into the rest of the part. Finally, if we have multiple parts, based on the infrared footage, I would suggest that printing one at a time, rather than several on a plate, will minimize the time the previous layer has to cool before the hot nozzle is in contact with it again. There are much more advanced techniques than these, and to learn about them I would recommend the channel CNC Kitchen. In one such experiment, Stefan printed some parts, encased them in salt, remelted the parts inside the salt in an oven, and then compared the raw versus the remelted parts in terms of appearance as well as strength. If you're looking to push the limits, that's one possible method, but this video is aimed more at beginners, who hopefully now can see the link between woodworking as well as 3D printing and have some more tools in their toolbox to be able to print strong parts. Let me know in the comment section if this was useful or if you've got some great tips to share with your fellow viewers. Thank you so much for watching, and until next time, happy strong 3D printing. G'day, it's Michael again. If you liked the video, then please click like. If you want to see more content like this in future, click subscribe and make sure you click on the bell to receive every notification. If you really want to support the channel and see exclusive content, become a patron. Visit my Patreon page. See you next time.